Okay, so yeah, we're doing indeterminate forms. And so what I mean by indeterminate form is if you get like, so here, let me give you a quick example. So if I tell you, if I give you something like the limit as x approaches 1 of x squared minus x over x squared minus 1, when you try and plug 1 into here, you're going to get 0 over 0, right? And so this right here, this 0 over 0 is an indeterminate form. So it's basically like when you get a limit is equal to something that's essentially not possible, right? And so here, that's the very first type of indeterminate form. So the first one is the form 0 over 0, or infinity over infinity. So you kind of take care of these two the same way. Here, I'm going to actually write them as separate ones just because they are different forms. Right, so what is 0 divided by 0? What is infinity divided by infinity? And so those are the first two types of indeterminate forms. The third type is, I want to say, yeah, it's 0 times infinity, right? You would think this is 0, but it's not always going to give you 0 when you evaluate these limits. The next kind is infinity minus infinity. Actually, you know what? I was trying to do it this way because I thought it would look better for the video, but now I just have a lot of white space. So I'm going to rotate my screen again. Is this okay for everybody reading it like this, or is this too small? Oh, this is tiny now. Yeah, zoom in a bit. Oh. Yeah, okay, this is acting really strange now. I can't zoom in. There we go. Okay, so here, here's what I'll do. There you go, is that better? Okay, yeah, so I just made everything really big. All right. Infinity minus infinity, let me talk about that one real quick. That's not equal to 0 either, because you could have something where like maybe one infinity, and I think I talked about this in class before we went online, but you could have one infinity is like 3 trillion, and then maybe the other infinity is like 1 billion. And when you subtract those, you're not getting 0, right? And so that's one type of indeterminate form, is because you don't actually know what infinity is, right? And then the last 3 are also very similar. You kind of take care of them the same way. And so I'll write them as separate ones, but you're going to have 0 to the power of 0, right? Because usually anything to the power of 0 is 1, but why would 0 to the power of 0 be 1? And then you have infinity to the power of 0. And then the last one is going to be 1 to infinity, which you would expect to just be 1. But when we start to do the examples, I'll talk a little bit more about this. But so these are the different types of indeterminate forms that you could see. And so these are going to be like, if you get a limit is equal to something of this form, then that's indeterminate. So are there any questions about this or about these forms? Okay, so first let's talk about indeterminate forms 0 over 0 and infinity over infinity. Okay, so basically the reason for that is essentially, here, I'm trying to think of how the best way to put it. So like, right, if you look at this limit right here, so here, let me put this all in blue and then I'm just gonna erase this later. But if I look at this limit right here, so the limit as x approaches 1, x squared minus x over x squared minus 1, you should be able to split that up as the limit over the limit, right? And so the problem here is that if I were to evaluate these two limits separately and then divide them, I might not get 0 over 0. And so just because that's what it looks like I'm getting doesn't mean that's actually what I'm going to get when I split them up. And so the same thing is happening here. If I have like the limit of f times the limit of g, it might not look like it equals the limit of f times g, which is kind of strange, I know, but that's why we're going to learn the L'Hopital's rule, because there are ways to get around this, right? But does that kind of help, Simon? Same thing down here too, like with the limit of 1 to, or this last indeterminate form, 1 to infinity, if I have like the limit of f to the power of g, it might not equal limit of f to the limit of g. And that's essentially what's happening here. And so, yeah. Okay, so let's look at the first kind and see how to solve it. And so, hang on real quick. Yeah, let's look at this example we had looked up here and figure out. So if I do this one, without knowing what L'Hopital's rule is, how would you guys want to solve this? Like what should I do to both pieces here? Yeah, you can factor. So the top, I'm just going to factor out an x. So I get x times x minus 1. And then the bottom, I get x plus 1 times x minus 1. And so now I get that the limit is actually equal to 1/2. Right, and so here, I could just easily factor and get my answer, but that's not always going to work, right? And so an example of where that does not work would be, what if I give you the limit as x approaches 1 of ln of x over x plus 1. When I plug this in, if I do try and plug x equals 1 in, I am going to get 0 over 0 because ln of 1 is equal to 0, right? Oh wait, I don't get 0 on the bottom here, so I think this should be x minus 1. Yeah. And so factoring won't help. There were other methods in the beginning that we had used. Like if we tried multiplying by the conjugate, maybe that would work, but that doesn't work here either. And so the methods that we had seen before don't work, right? And so let's kind of write that down. So factoring, multiplying by the conjugate, and other methods from the beginning of class, or other methods from earlier sections, do not work. So let me show you what L'Hopital's rule is then. So L'Hopital's rule, and some people, like I think on your homework, it's spelled La Hospital, but it's always pronounced L'Hopital. So L'Hopital's rule says, suppose that f of x and g of x are differentiable and g prime of x does not equal 0. Okay, so not a comma, but a period. And then we're also going to suppose that the following four limits are true. So suppose you have that, hang on, the limit as x approaches c of f of x is equal to 0. Oh, whoa, no, thank you, Siri. That the limit of f of x is equal to 0, and the limit as x approaches c of g of x equals 0. Then what L'Hopital's rule really is that, so then the limit as x approaches c of f of x over g of x is equal to the limit as x approaches c of f prime of x over g prime of x. This also works, so this also works if these two limits that I have up here, the limit of f equals 0 and the limit of g equals 0, if they're both equal to either positive or negative infinity. So also works if the limit as x approaches c of f of x is equal to positive or negative infinity, and the limit as x approaches c of g of x equals positive or negative infinity. Do you think I can use this rule if I have like this piece, so the piece that I'm underlining in blue combined with this piece? Can I use L'Hopital's rule then if I have like 0 over infinity? Yeah, no, I can't, right? So it has to be these specific pairings. They're either both 0 or they're both infinity. And so let's look at the example earlier that we couldn't do. Oh, you know what? Here, there's one thing, there's another note I want to make about this. So note, oops, I don't want to write it in blue. This rule works for x approaching c from either the positive side or the negative side, and if x is approaching either positive or negative infinity. So this works like kind of regardless of what you're approaching, right? It's not just that it has to be a real number, it can be infinity and it can be approaching from one side. But so let's look at the example that we couldn't figure out how to do earlier. So if I give you the limit as x approaches 1 of ln of x over x minus 1, I'm going to use L'Hopital's rule. And so if I had to pick an f of x here, what would my f of x be? Like if I kind of compare it to what I'm doing here in the place that I just starred. It wouldn't be 0. Well, it would be 0 when I plug in 1, but if I don't, like, so that would be f of 1 would be 0, yeah. So f of x would be ln of x, and then f prime of x, hang on. What's f prime? What's the derivative of ln again? Yeah, it's 1 over x. And so my g of x then is just going to be the denominator. So this is x minus 1, which means g prime of x is just going to be 1, right? And so L'Hopital's rule really says that if I look at the limit as x approaches 1 of ln of x over x minus 1, what I'm really looking at, or what I can look at instead, is the limit of 1 over x over 1. And here, when I plug 1 into this, I just get 1. I don't get 0 over 0. And so what some people will do is they'll just put a little L-H there to kind of say, like, this is where I used L'Hopital's rule. That's what's happening here. And so I think it's kind of good to get in that habit, just because when you're doing like really long things, it's kind of nice to be able to keep track of what happened where. But so are there any questions about this example? Okay. So then let's do another one. Let's find the limit as x approaches positive infinity, oops, of e to the x over x squared. Here, what happens if I just try and plug in infinity? What am I gonna get? What's e to infinity? So e to infinity over infinity squared is gonna give me what? Yeah, you would get infinity over infinity, right? Because the graph of e, as x gets really large, y gets really large too. And so here you're getting infinity over infinity, so we're going to use L'Hopital's rule. And so I'm going to have that the limit, and so what I did up here with this whole identifying f and g, you don't have to do that every time, right? But you can if you want to. And so here I'm going to kind of skip it. If you want me to start doing it again, just let me know. Remember, you can send private chats too. But so here, the limit as x approaches infinity, what's the derivative of e to the x again? Yeah, it's just e to the x. And then what am I going to get on the bottom? Yeah, 2x. And so here, I use L'Hopital's rule again, but what happens when I try and plug in infinity now? What am I getting now? If I just try and plug in infinity, did it solve any problems, essentially? Yeah, no, I'm still getting infinity over infinity. So are there any ideas? What can I do here? Yeah, exactly. What's to stop me from looking at this as f over g and then just using L'Hopital's rule on that one, right? And so we're just going to do L'Hopital's rule again. And so here I'm going to have the limit as x approaches infinity of e to the x over 2x. We already saw that the derivative of e to the x is just e to the x, but then on the bottom here I'm just getting 2. And so again, I use L'Hopital's rule right here. And now when I plug in infinity, I'm not getting infinity over infinity, I'm getting infinity over 2. And what can I just say that's equal to? Yeah, it's just equal to infinity, right? And so our answer here is actually infinity. So are there any questions about either of these examples that are up here right now? Okay. Then I want to say there's one more type of problem I wanted to look at before I move on to the next kind. Okay, yeah, here. So let's do this one. Example. So let's look at the limit as x approaches infinity of ln of x over the cube root of x. And so here, when I just try and plug in infinity, I'm actually going to get infinity over infinity again, right? And so I need to use L'Hopital's rule. And so the limit as x approaches infinity, ln x over the cube root of x, this is going to equal the limit as x approaches infinity, 1 over x, and then what's the derivative of that cube root of x going to be? I can kind of do it off to the side. So I know that g of x is going to equal the cube root of x. And I can rewrite this as x to what power? Yeah, to the 1/3 power. And so that means g prime of x is going to be 1/3 x to the negative 2/3. And so this derivative, if I write it a little bit nicer, is going to be 1 over 3x to the 2/3. And so here I'm going to have 1 over 3x to the 2/3. This right here is where I L'Hopitaled it. When I have a fraction over a fraction, what can I do with these two pieces right here? What am I really multiplying this top one by? It starts with an R. Yeah, the reciprocal, right? And so what I really have here is 3x to the 2/3 over x. And that's just because if I do this in blue, I'm just kind of multiplying by 3x to the 2/3 over 1 over 3x to the 2/3 over 1. And here they cancel out, and then here on the top, this is where I get my result down here. All right, so then here, quick question, do we need to use L'Hopital's rule again? Yes, you would expect to because you're getting infinity over infinity, but I also have x over x. It's x to the 2/3 over x, but that's fine, right? And so remember, if I have like m to the, or here, p to the power of m over p to the power of n, what can I do with those two exponents? It's the opposite of add. Yeah, you would subtract them. When you have p to the m times p to the n, that's when you get p to the m plus n. But with division, you'd subtract them. And so here, oh, Siri, go away. I can do the limit as x approaches infinity of 3x to the 2/3. And here I can think of it this way, minus x, or not minus x. I don't even need that parenthesis, minus 3 over 3. Is everybody okay with that? Like, does this make sense? Okay, yeah, and so this 3 over 3 just came from the fact that that's x to the first power, and I just made that 1 a 3 over 3. And so then here, this is really equal to the limit as x approaches infinity of 3x to the negative 1/3 power, which if I simplify that one more time, I get 3 over the cube root of x. And so now when I plug in infinity, what am I getting? You get 3 over infinity, which is equal to 0. Yeah. So remember, right, like if I have 3 over 4, that's 0.75, but if I have like 3 over 6, that's 0.5. And so the bigger my denominator, the smaller my number. And so if my denominator is 0, then my number is going to be as small, or if my denominator is infinity, then my number is going to be as small as possible. And if my denominator is as small as possible, then my answer would be infinity. And so here, this is the answer to that limit. Oh, and the answer to this question would be no. but you could use it again if you wanted to. So are there any questions about this example? Does this make sense for everybody? So yeah, it's really just putting into practice our limits and our derivatives, right? So you're kind of combining them now. And so here, the next thing we're going to look at is the indeterminate form of 0 times infinity. And so can I scroll? Am I going to leave anybody behind if I... Here, I'll move it like this. That should be fine. So let's now talk about indeterminate forms. Oops. Zero times infinity. And so the very first thing is if the limit as x approaches c of f of x times g of x is equal to 0 times infinity, what you're going to do is you're going to rewrite f of x times g of x in one of the following ways. The first way is you're either going to take f of x times g of x and write it as f of x over 1 over g of x. So you're going to flip either f or g, and so yeah, it's the second way is when you flip f. You either have g of x over 1 divided by f of x or f of x over 1 divided by g of x. And that's going back to the same kind of rule or the same kind of thing that I did up here where I'm going to star in green, right? If I do multiply by the reciprocal of my denominator, then that would just be multiplying by g over x. And those things would go away and I would get f times g, right? You can do the same thing with that second one. But so that's how you're going to do it. So let's see an example of that. And oh, what this does, so these conversions, I guess is the best way to call them, will result in either 0 over 0 or infinity over infinity. And then you use L'Hopital's rule. So you're essentially putting it in a form so that you can use this rule, which is a really, really nice rule to have, right? And so let's look at an example. Let's look at the limit as x approaches 0 from the positive side of x times ln of x. And so here I can't just use L'Hopital's rule because I don't have a fraction and you need to have an f over g in order to use L'Hopital's rule. If I tried to use L'Hopital's rule right now, I could think of this as over 1, but then when I try and take the derivative of this piece, you're just going to get 0. And you can't have 0 in the bottom, right? So we're going to need to use one of these two things up here at first, right? And so you kind of have to pick and choose which one of these do you want to flip and which one do you not want to flip, right? And so if we flip, okay, so our options, so what I mean by that is our options here are to either write it as ln of x over 1 over x or x over 1 over ln of x. And so when you write both of these out, you kind of have to think about the next piece of this, right? So the next piece of this would be using L'Hopital's rule, which means I have to take the derivative of both the top and the bottom. And so in which case of these, so I'll call this case A and case B, which one of these looks nicer for taking the derivative of both of those pieces? Yeah, definitely A, because if I look at B, then I'd have to differentiate 1 over ln of x, and that's going to get really messy, right? Because then I'd probably have to use the quotient rule. So it would just be easier to go with option A. So option A is easier to differentiate, so I'm going to use that one. So is everybody okay with these two different options and why I have them and what they're doing? Okay. Yeah, so then here I'm going to have the limit as x approaches 0 from the positive side of x times ln of x. Well, that's really equal to the limit as x approaches 0 from the positive side of ln of x over 1 over x. And then now is when I'm going to use L'Hopital's rule. And so this is where it comes in kind of handy so that you can actually write, like I'm going to put this LH right here. And that way I know that's where the L'Hopital's rule came in. And so I'm going to have 1 over x. And then what's the derivative of that 1 over x going to be? Yeah, negative 1 over x squared. And so here, when I try plugging in 0 now, I get 1 over 0 over 1 over 0 over negative 1 over 0. So what am I getting here when I try and plug this in? I think you're technically getting infinity over infinity. But either way, you're still getting something that's not nice to work with, right? And so, like, basically I can't plug 0 into it just yet. So I can do something that makes it a little bit easier to work with. And it's going to be the same thing that we did in the last example, right? Where this kind of thing, where I take it and I don't want 4 or 3 fractions. I just kind of want 1. And so I can rewrite this as negative x squared over x. Does everybody see that? Okay. And so yeah, here, let me kind of do it in blue real quick. So this would just be multiplying by the reciprocal of the denominator. And so these things cancel. And then here, this is what results in my fraction down here. But so then when I simplify this even further, I just get negative x. And so what's the answer to this limit? Yeah, it's going to be 0. So this is one case where 0 times infinity turned out to be 0, right? Because up here, if I had just plugged this in, I would have gotten 0 times infinity. But it's not always going to work out that way. So are there any questions about this example or about this indeterminate form? Because I'm going to move on to the infinity minus infinity now. Okay. So here, I'll leave this here. The indeterminate form infinity minus infinity. Again, what we're going to do is we're going to essentially try and convert this to either 0 over 0 or infinity over infinity. And then we can use L'Hopital's rule. So that's essentially what's going to happen to all of these other indeterminate forms is we're going to convert it back to one of the first two. And so here, this type of indeterminate form happens when you when you have something that looks like f of x minus g of x, right? And so what you want to do is you want to convert to either 0 over 0, oh geez, 0 over 0, or infinity over infinity by either using a common denominator rationalizing or factoring out a common factor. And there are probably other ones. So I'll put etc. So let me kind of show you what I mean by that. So let's do an example. So we're going to look at the limit as x approaches pi over 2 from the left of secant of x minus tangent of x. So, real quick, sorry, it hit my knee. Real quick, I'm gonna draw the pictures for both secant and tangent. So tangent, if you remember, so here's pi over 2. It has an asymptote at pi over 2 because tangent of pi over 2 is undefined. And so if I look at tangent, it looks almost like the cubic in the middle, right? And so on the left side of pi over 2, what's happening to tangent? What is it going to? Yeah, it's going to positive infinity, right? And so that's tangent. If I draw the one for secant now, yeah, because pi over 2, this would be pi over 2, so then pi over 2 from the left would be like the negative side of pi over 2, right? Oh yeah, so this right here is pi over 2 from the left, yeah. And then this graph of secant, since secant is 1 over cosine, and cosine of pi over 2 is 0, I have an asymptote here again for the graph of secant. And on the negative side of pi over 2, that's when I have that graph, right? And so this is secant. And so what is happening to secant on the negative side of pi over 2? Yeah, it's also going to positive infinity. And so what I have here is if I just try and plug in pi over 2 on the negative side, I'm getting infinity minus infinity. And so if you look at the 3, I gave you 3, so using a common denominator, rationalizing, or factoring something out, which one of those methods do you think I'm going to use here? So think about what you can do with the trig functions, right? So to make this graph, I had written that down. Yeah, it's gonna be a common denominator, right? And so let's write that out. Common denominator. So don't forget with trig functions, you can always write them as fractions of other trig functions. And so for my common denominator, I get the limit as x approaches pi over 2 from the left. How do I write c? Oh, well, secant I just showed you. It's 1 over cosine. But then tangent, what is tangent? Yeah, it's sine over cosine. And so here, they actually already have the same denominator. And so it makes it a little bit easier. And so the limit as x approaches pi over 2 from the left, it's really just equal to, I don't need that big parenthesis, 1 minus sine of x over cosine of x. And so what happens if I try and plug in pi over 2 here? What is sine of pi over 2? Yeah, it's 1. Cosine of pi over 2 is 0. That's why we have an asymptote on the graph of secant at pi over 2. And so what I'm getting here is I'm getting 0 over 0. And now, what can I do with this? Yeah, I can use L'Hopital's rule. And so here, you're going to get the limit as x approaches pi over 2 from the left. What's the derivative of sine again? Positive or negative cosine? It's positive cosine, but then I have this minus here. So I'm actually going to have negative cosine, right? But then for cosine, the derivative has to be negative sine. So if the derivative of sine is positive cosine, the derivative of cosine is negative sine. And so what is this really equal to? Yeah, it's cotangent, right? And so in here, this is where I did L'Hopital's rule. But this is positive cotangent. If you look at cotangent of pi over 2, you could also, if you don't have to write it out like cotangent if you didn't want to, if it makes it easier, if it's easier for you to just plug pi over 2 into cosine and sine, that's totally fine. But yeah, this is, when you simplify it, it is cotangent. And cotangent of pi over 2 is actually equal to 0. So are there any questions about this example? Okay. So far that takes care of, hang on, I'm gonna scroll back up real quick. That takes care of 1, 2, 3, up to 4. So we've learned how to deal with 4 of the types of indeterminate forms now. And so let's talk about the last 3. They're all solved the same way. And so what we're gonna do, so I'm gonna scroll a little bit. So if I have indeterminate forms, zero to the power of 0, infinity to the power of 0, and 1 to the power of infinity. What you're going to do is, so this basically happens when you have something like the limit as x approaches c of f of x to the power of some function g of x, right? That's when you're going to see these indeterminate forms. And so when this happens, what you're going to do, so rewrite as f of x, oh no, not f of x, sorry. What you're going to do is you're going to either take ln of both sides, or not both sides, but either take ln or write it as an exponential. And the more common one you're going to see is an exponential. So what you would do is you would have, oh geez, Siri, stop. F of x to the power of g of x, you would say that that's equal to e, and then you would have g of x ln of f of x. And so I have some composition going on in there. But so essentially, to show that these two sides are equal, right? If you look at this right here, the exponent on that, essentially what you can rewrite that as is ln of f of x to the power of g of x, right? Because the ln rule says bring powers down, or yeah, bring exponents down as like the coefficient, right? And then what is e to the ln? Like if I gave you e to the ln of x, what should you tell me that that's equal to? Not 1, but whatever's inside of there. So it would be x, right? And so here, this time, it would be whatever's inside of here. So it would be f to the power of g. And so that's why these two things are equal. Is everybody okay with that? So essentially what I did was I took the ln of f of x of g of x, and the ln rules say I can bring that down, but that's not equivalent to what I had before. So to make it equivalent, I can just take the e of this, and it kind of undoes that ln. And so that's why those two things are equal. There's a better explanation. So is everybody okay now with why this equality is true? Okay, cool. I'm gonna erase all of that. It'll all be in the YouTube video, so. Okay. So then here, let's do an example. So the example we're gonna look at is the limit as x approaches 0 from the right, so the positive side, of 1 plus sine of 4x to the power of cotangent of x. So here, when I try and plug in 0, what's gonna happen? I'm gonna get 1 plus sine of 0, and sine of 0 is just 0, so I get 1. And then does anybody know what cotangent of 0 is gonna equal? I'll give you a hint if you look at the indeterminate forms we're looking at. It's actually positive infinity on that side. It's negative infinity on the other side of 0, Jennifer, right? Because the graph of cotangent, what it does is I have an asymptote at 0, and on this side of it, it goes towards positive infinity, but on this side of it, that's where it goes towards negative infinity, and we care about this side of it right now. So it's gonna be positive infinity. And so here, you're getting 1 to the power of infinity. And so I'm gonna have to take it and write it like that, essentially. And so here is how, okay, so this, I didn't do it that way in my notes, but let's try and do it that way. So if I take 1 plus sine of 4x to the power of cotangent of x, well, I can say that's equal to e. And then what's g of x in this case? What's gonna go first right here? Yeah, it would be cotangent. So e, oh, that looks like a capital C. E to the power of cotangent x. Hang on, I'm writing kind of small. Let me write this bigger. And then ln of that 1 plus sine of 4x. And so now, since these two things are equal, I can take the limit of this second part. Ow! Oh, excuse me. So e to the cotangent x ln of 1 plus sine of 4x. And so one thing you can do with this is I can actually move this e out and just take the limit of the power. I think this is one of the limit rules we had talked about a long time ago, but I don't remember. But this is something that you can do. And so here, I can just look at the limit as x approaches 0 from the positive side of cotangent of x times ln of 1 plus sine of 4x. And so really what I'm going to do now, and I'll put this in red, is I only care about this piece. I only care about the exponent on this e, right? I don't care about that e for right now. And so I don't want to keep writing it as an exponent, so I'm just going to bring it down. And I'll just focus on that limit for now. Cotangent of x ln of 1 plus sine of 4x. Oh, sorry, Grandpa. I'll call him back. Okay. How can I make this look like a fraction? Do you guys have any ideas? Because remember, the goal is to get it to look like either 0 over 0 or infinity over infinity. And right now, I'm not going to get either of those things. So how can I change this slightly so that I do get a fraction? Remember your trig rules. What can I do with that cotangent? Yeah, how is it, what is it gonna, I can either do it as cosine over sine, or I'm actually just gonna do over tangent. That way, because if I do cosine over sine, then what I'm gonna have is I'm gonna have oops, what happened? I'm gonna have cosine of ln over sine, and then in the top, when I do when I differentiate, I'm gonna have to use the product rule. And so if I just make it tangent, if I just make cotangent 1 over tangent, then I don't have the product rule in the top. Does that make sense? So it's just a little bit easier, but cosine over sine would definitely work too. So here, ln of 1 plus sine of 4x over, not cotangent, tangent. And then when I try and plug 0 into here, you end up getting 0 over 0. And so now I can use L'Hopital's rule. And this one gets a little ugly, right? Because I have the chain rule in this one. And so I'm just going to kind of give you the derivative, but I want you to double check this later, right? But the derivative of the top is going to be 4 times cosine of 4x over 1 plus sine of 4x, right? The derivative of ln is 1 over whatever's inside, and then you take the derivative of what's inside. And so that's how I got 4 times cosine of 4x. So that's just the derivative of ln. And then now I need to worry about the derivative of tangent. What's the derivative of tangent again? It's actually positive secant squared. The derivative of cotangent is the one that's negative, and that's negative cosecant squared. But so yeah, here it's just positive secant squared of x. And so now when I try and plug in x equals 0, I know it looks kind of ugly like this, but when I try and plug in x equals 0, I don't get any problems. I get 4 cosine of 0 is 1 over 1 plus cosine of 0 is 0. And then secant of 0 is actually 1. And so here, all of this just gives me 4. So my answer is 4, right? I'm done. It's 4. I'm done with the problem. I can walk away. Is that right? No. What am I forgetting about? Yeah, that E that I kind of started ignoring at some point, right? And so here, what I need to do now is I need to say, okay, but that was just for this part, right? This star was just for that part. And so my answer is really E to the power of 4. So the limit as x approaches 0 from the positive side, oh geez, sorry guys. 1 plus, oh my goodness. Okay, I'm gonna scroll up because it's running right at the bottom. 1 plus sine 4x to the cotangent of x. This is equal to e to the 4th power. And so this is actually, I feel like all the other examples, like when we did 0 times infinity, it was telling you it's not 0. When we did infinity minus infinity, I told you it wasn't 0. But the 2 examples we did were bad examples of what I had told you. And so here, this is a perfectly good example. 1 to the power of infinity did not give us a result of 1 when we actually went through and did the problem, right? And so before I let you guys go for today, I want to talk about the different types of things you can have with this. And so here, so question, or not here, I'm not gonna word it as a question, I'm just gonna show you the answer. But so, example, I'm gonna let f of x equal 1 plus 1 over x. Oh, I don't need that parenthesis just yet. But so yeah, f of x is going to be 1 over 1 plus x. So then when I look at the limit as x approaches infinity of f of x, I'm going to just get 1, right? Because I would get 1 plus 1 over infinity, but 1 over infinity would give me 0. And so here, to kind of see why 1 to the power of infinity is not going to give you 1, let's look at the limit as x approaches infinity of f of x to the power of x. Here, you're actually going to get e, right? And so if you were to do this problem the same way that we solved this example that we just did up here, you would get an answer of e. And so this is also like, it results in 1 to the infinity before you do all of that work. But after doing all of that work, you're going to get e and not 1 to the power of infinity, or even 1, right? And so I'll show you 3 more. So the limit of f of x to the power of the square root of x, when you do the whole logarithm and e conversion, you get 0. If I look at the limit as x approaches infinity of f of x to the power of, I don't know, 2a times n, where n is just some power, and then a is a coefficient, you're going to get e to the power of a, which is also not 1. And then the last one is if you have f of x to the power of n squared, you're going to get infinity. Right, so there's 4 limits where when you start out, it looks like you would get 1 to the infinity. But when you actually go through and do all of the work, you don't get anything that looks even remotely like that, right? And so here, the note I kind of just want to make is, so note the value of a limit of f of x does not alone determine the value of the limit of f of x to the power of g of x. So are there any questions about this? Or about anything that we talked about today? All right, so I'm gonna stop the recording.